Hello, this is Mike, and welcome back to our ongoing Godot tutorial series from Gamefromscratch. Today we're going to be taking a look at two subjects that are related but not quite identical, collision detections and physics simulations. I say they're related because when you get into physics it will handle collision detection for you, but you can also, and quite often will want to, check for collisions without necessarily requiring a full physics simulation. Pretty much, if you've never used a game engine in the past that has a physics engine in it, the way they work is kind of by trying to simulate real-world physics mathematically. So what you do is you create a number of different objects. I'll explain what those objects are a little bit later on, that are part of the physics simulation. And then each frame or each update, it goes through and calculates what particular movements should happen. You then take those movements that apply to these objects and you apply them back to your game sprites. So that way, say for example, if you had a ball and you wanted to bounce, you would apply some physics to the ball sprite to say this is its mass, this is how bouncy it is, and then you would let it go. And then the world's gravity would kick in, and then it would fall until it hit something, at which point it would calculate the bounce. And then each one of these updates, the physics object itself is getting updated its location, and then that gets tied back to your sprite. So in the long run, is what you're doing is you're basically mathematically calculating the movement based off the physics of your world. Now, collision detection is a different thing altogether, sort of. Collision detection is simply detecting if two objects collided with each other. You'll use this all the time in all kinds of programming, from simple checking if a raycast or a pixel is within certain bounds. For example, if a user clicks on a button, that's an example of collision detection. Determining if two sprites ran into each other, that's a type of collision detection. Now, like I said, the physics engine has all the functionality you need to do collision detection tests and more. However, a lot of times that's actually complete overkill. So first we're going to look at just calculating a collision between two objects to start with. It's going to be a little convoluted, and one thing to realize is later on down the road, when we actually get to the physics engine, the collisions are done for you. It's actually a lot simpler. So this is going to look a little bit more complex than it is. But let's jump right on in. Just a second here. I'm going to adjust my mic. Hopefully that's a bit better. Okay, so I've loaded up Godot here. First thing we're going to do, we're just going to create a very simple scene. Let's see. First, let's just add a node at the top. And we will add two sprites to the world. Alright. Sprite 1. And we'll be using this guy a lot. We'll just use the icon that ships with it. Let's relocate him, like so. And let's go ahead and create another sprite. We'll relook. Ooh. Let's give him like so. Bring him over here. Oops, my bad. I parented it. Did not want that. All right, let's try that again. Now, let's go ahead and load the texture. Okay, so now we've got two sprites in our game world, and what we want to do is just move this one over until it hits this one, and then we're going to check for a collision, and when it does, we'll just start it back to the starting position where it came from. And we're just going to do this over and over and over again. I don't like having spaces in my name, so I'm an old school Unix guy that way. I find they cause more problems than worth, but there's no actual reason not to. I'll just change that guy to sprite 2, no space. Alright, so I need to set my scene up. So first we need to save it. That's fine, and then set it as the active scene. Again, if any of this doesn't look familiar at this point, go back through the old tutorials. This is all covered. I'm only going to cover new stuff as we go through it. Alright, so now we need to attach a script to this guy to get it moving. So let's go ahead and give it the incredibly horrible name of Sprite1 script. Alright, so let's get to work. First thing we want to do, I'm sorry, I can't, there's no ability for presentation mode, so I can't make this code big or easier for you to read. However, if you go to gamefromscratch.com, there's a corresponding tutorial that has all of the source code listings I'm doing here available there. So if you can't see what I'm doing here, just go to Gamefromscratch. You can get the source code there. It'll be linked in the comment below, or the description below. So first thing we need to do is set up so that we get updates each frame, like so. And now we're going to need, obviously, the process function. Oops, hit my caps lock key. So, all right. Now, we're going to need a couple of variables. Your collision detection, actually, I'll get to that in a second. Built-in type of vector2. This is just the initial position where we're starting from. So when we reset it later on, we'll have it there. And then we're going to have box1 and box2. These are our collision volumes. We'll see that in a second. Actually, we'll see that right now. So first thing we're going to want to do is just grab our start position, like so. And then we're going to want to create the two collision volumes. They are rectangle shape 2Ds, like so. Now, the shape 2D class is what you use to define a shape in 2 dimensions. There's the 3D equivalent of it as well. And there are a number of different options. Things like bounding box, or in this case called a rectangle shape, the bounding sphere, which I believe is called circle shape 2D. There's a capsule. Then there's convex and concave polygons as well. Each one of these is used to define just basically a shape in general. These are what we're going to actually, so your sprite itself is just a graphic. There's no real dimensions to it in the world. So these shapes are going to say, these are the dimensions of my sprite. Now we're also going to use the texture resolution to determine what they are. But to do your collision math, you need to use shape 2D derived classes, such as, for example, this rectangle shape 2D. So that's what we're going to do. So we're going to create a box for that are going to represent the dimensions or the location of I suppose the boundaries of both of our sprites. So that's what box 1 and box 2 are. Alright. What did I do wrong? Oh, I typoed. Okay, let's try that again. There we go. Okay, so all we're done here is we get our initial position and we create two boxes. So we haven't defined them yet. We'll define them actually on each frame because as you could potentially be changing your sprite. As a result, you could change your dimensions ultimately. Chances are that wouldn't actually happen, but doing it on a per frame basis isn't a terrible thing. It's not that slow either, so it's not really something you need to watch out for. So the first thing you're going to want to do is get a reference to our other sprite. And it is, I believe, called sprite 2. Actually, you know what? I'm getting in a new habit giving things slightly better names, and for hierarchy, making my hierarchies all start from node, because I find you're going to want to reparent things. You can only ever have one top level node as your parent, and I find it's constantly later on down the road I want to change it. So making it a node that does nothing your parent seems to be the most effective way to use Godot. So that's what I'm doing. And then the name node is not particularly good because it's used a lot. So I've been getting in the habit now of changing it to a scene root as my name. You can call it whatever you want. It's just when you now call your get node to get the other sprite, you're going to have to keep that name in mind. So it's off root, and now it's called scene root, like so, and it is called sprite 2. Again, if you didn't take the space out, you would obviously put the space in right here, but this is going to get a reference to the other sprite class. And now what we need to do is, let's move ourselves 0.1. So we're going to move each update 0.1 pixels to the right. Update's called a number of times per second, so this is actually going to be a fairly fast move rate. And you could probably normalize it based off the delta, but I'm not going to get that sophisticated in this one. Okay, why are you indenting? Oh, because you don't actually exist. Alright, I forgot to put the coordinate. Move local x. Alright, so now what we want to do is define our box. So our first bounding box, we use the method set extend. Why are you mad? Oh, I'm indented wrong. Oops. Alright, see if it's happy yet. Alright, why are we upset at this point now? I've done something wrong. I don't know what it is specifically yet, but I'll find it in a second. Error parsing. Okay, it might be back now. Okay, so this takes a vector 2. It probably takes a little bit of explanation of how you're defining the extents of your rectangle, and more or less you're giving it a width and a height relative to its center. So basically what we want to do is get the texture of our sprite itself and figure out what its width and what its height are, but obviously we only want to have that because the dimensions for the rectangle shape 2D are relative to its middle. So basically you pass in half width, half height to create the rectangle. So then we want to pass in get texture, and then get size, and then height. Oh, no, sorry. And then width, div2, and get texture, get size, height, div2. So that's our vector 2. We're going to create the extensive, like so. And now we want to create the second bounding box. Same deal, vector 2. Only difference is this time we are now using sprite 2's reference. Get texture, get size, width, and sprite2.get texture. Obviously something's gone wrong there. Sometimes it's not the friendliest code editor for figuring out why it's not happy. That sprite2.get texture. Yeah, that should just work. My node type for some reason is returning the wrong type, but it shouldn't be. Okay. So in theory, so what we've now done is we've created 2 bounding boxes based off the extents of each of our textures, texture map. Now, obviously in this case, we've used the same texture, so we could technically use the same box. But in most real-world cases, you've actually used 2 different images, and you would have 2 different dimensions, etc., which is why I've done it as 2 different texture boxes. So now that we've got them, what we need to do now is just see if there's a collision. We're checking, again, this is processors. We need to run each frame. So we just come down and go if box 1 dot collides, and then what you're passing in now is the matrix 3 transform for each of the entities, and then the box, the second bounding box to check against. So we just do get transform, so that's the coordinates of the first sprite, box 2, so that's the bounding box of our second sprite, and then sprite 2 dot get transform, like so. So if there is a collision, then we will set our position back to the start. That's it. Now there's obviously an error here because it's not liking sprite 2. Scene root sprite 2. I'll go ahead and run this and see what it does. Collides. Oh. Yeah, let's get rid of the S and use a function that actually exists. And there we go. And if I've done this right, boom, back it goes. So that is very simple collision detection. Again, I might be able to show you on help quickly. All right, help. Let's find shape 2D. Shape 2D. All right, there's shape 2D. So far we actually just went ahead and used this rectangle shape 2D, which is a bounding box for, I guess, obviously, since each side is not the same size, a bounding rectangle. That's what we used for the dimensions. But if your sprite was more accurately represented by a circle or a capsule, which is like, what's the word? An ellipse, those would be what you would use instead. So it all comes down to like what the ultimate shape of your thing is. Segment shape, I believe, is a set of lines. Segment shape consists of 2 points. Okay, so it is actually literally a line. Ray shape would be, it's a ray cast into the scene. Normally you would probably use this for mouse picking. Line, I'm not entirely certain why line shape exists as opposed to segment shape, but we'll leave it at that. And then you've got concave and convex polygons. We'll actually see those in a little bit a little bit later when we actually get into the physics engine itself. So there are other shapes you can use, but the basic logic is exactly the same. They all inherit back from the shape 2D guy, and they all have a method called collide. And you can check for a collision between a rectangle and an array, or a rectangle and a circle, etc. And then there's some more advanced stuff like your custom solvers. You're probably not going to get into those. Also, you could get into context, which is how the things hit. Again, you're not going to get into those most of the time. What we've covered is generally what you would use when dealing with collision detection, unless you get more advanced and you start dealing with the physics engine itself, which is exactly what we're going to do next. So we're not going to cover that too much further. So simply that was collision detection in Godot. As you can see, you can roll these by hand. You can create these objects as you go. You just basically define it, set its extents, and then check for collisions. Done. Now, where this starts to fall apart and get really crappy is when you have 30, 40, 50, 60, 70 objects in your game and you're checking for collisions, because that's a lot of if-elses. And in that case, you're probably best to use the physics engine, even if you're just using it for collisions, because it will handle that for you. All right, so now let's move on to the physics engine itself. This is actually pretty cool stuff because it gives you a lot of power for almost free. And one of the nice things about Godot is sort of it's an all-in-one solution. So the physics engine is built right in. And a lot of times what you have is you use something like, say, Box 2D. It was one of the most popular 2D physics engines. And you slot that into your code. But then what you have to do is Box 2D will work in its own system. It's mostly metric. So it's in meters, etc. And then what you have to do is map it back to whatever pixel space makes sense to you. Godot works entirely in pixels, so it's quite intuitive. It's when you're working in the engine, if you say move by 90, it moves by 90 pixels. It makes the learning curve, the learning process, quite a bit easier. A lot of people get tripped up on the process with like integrating a physics engine using two different math coordinates. And it gets especially annoying when you start doing things like mapping from UI coordinate space, which might be the origins in a different location, to pixel space, and then casting that array into physics space, and then casting that value back to game space, and then back to UI space. And that's stuff you do all the time. And the all-in-one nature of Godot makes it so none of that stuff comes up, which is very nice. Okay, so that's one down. Now let's take a look at physics. Let's put this under video and create. Oop! Oh, that was dumb. All right, one sec. Let's try this again. Under video, create the folder called physics, like so. All right, so created a new project too. Actually, let's get this set up really quickly. So first things first, let's add our top level node. Call that scene root, and add okay, actually I can't go past that point for right now, so let's go ahead and save this and set it as our default. Getting sick of doing this yet? Alright, there we go. Should all be second nature at this point. So now we have it set up. It does nothing, but we have a single node scene set up ready for us to get physical in. Pun not intended. So now let's get back into 2D view over here. First thing we're going to do is we're just going to create a physical entity and have it apply to a sprite, and that's it. What we want to do is basically create it and then let gravity do its thing and watch it fall. Pretty simple. So first things first. What I would normally do is create a sprite at this point, but we're actually going to have the sprite being owned by something called a rigid body. Now, I said earlier that there are a number of different physics types available that are used in the simulation. Let me just go ahead and show you them as we're creating this here. Here we go. So physics body 2D, we have these three guys here, plus the area 2D, which is a little bit different, so we'll not cover it for now. But the three things to be aware of are your rigid body, your static body, and your kinematic body. Those are your three different kinds of entities that exist in the physics simulation. Now keep in mind, if you've got stuff that isn't physics related, it doesn't need to have anything to do with it. So let's say, for example, if you have buttons or entities in your world that don't interact with each other in any way, they do not need to have a physics body attached to them, or they do not need to have a physics body as a parent. This is only for physics-related simulations. So you can mix and match graphics that are not physically controlled and ones that are. So it's only things that will be updated by the physics engine that you need to attach a body to. Now let's cover very quickly what these three different things are and what makes them different. Start with static because it's the easiest one to explain. Static doesn't move. And that's the definition of a static body. It's basically the physics engine will interact with it, so other physical entities can hit a static body. However, the static body will not do anything. The nice thing about this is, and one of those things with the physics engine is, it's very CPU intensive. So the less calculation it has to do, the less CPU it's going to take up, which in turn means if you're working on mobile, less battery life drain, the device not getting as hot, and of course, everything else will run faster. So it is a somewhat important thing to not run too many intensive tasks. And a static body is probably the least intensive as they get. Generally what you would use a static body for is something like the Earth, bounds of your game screen, and I guess simply things that don't move. Another thing that you might use it for particularly is things that trigger. But this is what an Area 2D comes from, is that you can have physics entities as well that aren't part of the world at all, but they want to be aware of it. So if something hits them, it will trigger some code to run. So that's another thing that can happen. I'll cover that later on. But for now, be aware that there's the static body, and that is a physics object that does not move. Next up, you have a rigid body. A rigid body, kind of a strange name, because a rigid body can be very elastic, can be very bouncy. It's got nothing to do with the tacticity of the object itself. A rigid body is simply something that has a full physics simulation attached to it. The rigid body are the most CPU intensive, but they also have the most functionality. So rigid body basically has it's the full suite of things. It can collide with other rigid bodies. It can collide with kinematic and static bodies. It has you can apply forces to it. You can apply impulses to it, etc. So the rigid body is basically your physics entity. Now you don't want to have too many of these things. If you have a game with 300, 400, 500 of these things, it's going to probably grind to a halt. So you want to kind of keep them to a minimum. Now one of the nice things is you can sleep them. We'll cover that in a bit. But you can actually have them. So something's a rigid body, but only when it's actually awake is it going to take up a whole lot of processing power. Now finally, the last thing we have is this kinematic body. Kinematic body is, for all intents and purposes, your character for the most part. And there's a couple other things that you would use it for, but that would be the primary thing, is your game sprite. And the idea behind a kinematic body is, unlike the rigid body, the kinematic body you control the movement of. So you don't control it by saying, set impulses or applying force to it, or, giving it a weight and letting gravity take a hold of it. Instead, you're basically sitting there with your joystick or whatever, your keyboard, and you're saying move 6 in the X direction, move 3 in the Y direction. That's what you use a kinematic body for, is when you're actually controlling its movement. However, it's still going to interact with other things in the world. So that kinematic body can hit a rigid body. It can hit a static body. And it participates in the world. But the biggest thing is generally that you're controlling the movement there. All right, so that's an overview of what the different body types are available for simulation. Let's go ahead and start with a rigid body. So you make it the parent. Position it wherever you want in the world, like so. And now let's go ahead and, so I'll give you a quick view over here. These are the settings that you can set for it. All right, that's kind of pointless. Oh, where'd it go? All right, come on back. So you can set the mass and the weight. Now, at first glimpse, you would think, oh, wait, mass and weight are the same thing. No, they're not. Mass is more like physical dimension or boundary. It goes back to that whole expression of what falls faster, a ton of bricks or a ton of feathers. Well, obviously they fall at the same speed because they both weigh 1 ton. However, the mass of the one volume is going to be much larger than the mass of the other volume. So mass, think of it as terms of I usually think of mass, honestly, as density. So a denser, heavy object will fall faster. A higher mass object will, let's see, trying to get my math correct here, will fall slower. So the bigger an object is and the higher the weight is, the less dense it is. So anyways, that's the difference between mass and weight. Weight ultimately determines how much gravity applies to something, how much impact something has when it hits something else, etc. And then mass is basically you're indicating how big your volume is. Next up, you have friction. Friction is how two surfaces respond to each other. So when you run your hand across the top of a glass desk, you've got your skin has a certain friction volume and the glass has a certain friction volume. Now you take your hand and you run it across a brick uh, wall, for example, you're going to have a lot more resistance. You're going to move slower. It's going to take more force. That is ultimately what friction is. It determines the amount of friction on that surface. So it's mostly about how two objects will slide or interact with each other that way. Finally, you have bounce. In other physics engines, bounce is often referred to as restitution. The whole idea behind it is the amount of boing in something. So if you've got something that's a ball or something and it hits something else, bounce is going to determine how much counterforce is applied, so how much it goes back in return to that. Finally, you have a couple other settings here. We're not going to get into some of these until later on, if at all. But sleeping is what I was talking about earlier. Can sleep and sleeping is, if something's set to sleeping, it is no longer calculated in the engine. So you can turn things on and off, and like I said, that frees up the CPU processing quite a bit on the simulation. Next up, you have these velocities for angular and linear velocity. This is your angular is a direction of travel, whereas your linear velocity is the amount of speed you're going to start off going in that particular direction. The engine is ultimately going to calculate a lot of this for you. For example, when it applies gravity, it's going to apply linear velocity down the y-axis. But you can, if you want to set it to move right off the hop, you can set it by setting x and y velocities right here. Now this last guy right here is your layers. And layers are very important because what it is telling what will collide with what. So if two things are on the same layer, they will hit each other. But if something is on its own layer and nothing else is in that layer, because obviously you can have multiple layers. So if I put a layer here, like so, I will only hit things that are in this layer and this layer. Whereas if I do this, I will only hit things that are in the second layer. I'll go back to the first so I don't screw this up. Now where this gets important is when you start talking entities that shouldn't hit each other. Let's say you're making a shoot 'em up bullet hell kind of game, and you have hundreds of bullets flying around the scenes. And you're obviously going to want to check for collisions against bullets, but bullets shouldn't collide with other bullets, or bullets shouldn't collide with the world, or bullets shouldn't collide with. They should only collide with other game entities, and that's where these physics layers can come in. This is what is going to determine what can hit other things. So it's very important that way for determining, again, what can hit other objects and what can't, and also for speeding up your simulation. Because if you put everything in the same layer, everything can hit everything else, and that is quite often exactly what you don't want to do. All right, so now we've got a rigid body defined. Let's go back in here and just create a sprite, like so, and we will go use our trusty icon. Like so, and really that's it. So you've created your rigid body, you've applied a sprite to it, and done. Now I run it, and kaboom! There you go. You've created your first physical object. It's really that simple, which is kind of cool. And that's kind of the extent of it, to be honest. However, there's a lot more to going on, but that's how you define physics entities in Godot. You create the entity, you apply whatever the entity is going to be. Like in this case, my sprite is a child of that entity. So when my physics body is updated, it will update the position of its children, which in accordance here is our sprite. Now, what you might be wondering is, where did that gravity value come from? Why did it fall like that? What if I don't want gravity in my game, which is actually quite common? Let's say you're creating a top-down pool game. You wouldn't want all your balls falling for no particular reason. Well, these are set in your project settings. Go on in here and you scroll down. You shall find the physics 2D settings, which have your default gravity and your default gravity vector. Vector is basically saying that gravity applies along the positive y-axis. So as gravity is applied, your y position is incremented, which makes sense because this is y at 0, this is y at screen height. So if you wanted it to go up instead, you could turn this to a -1. If you wanted, for some reason, gravity to go left, you could switch this to 1 and 0. Like so. Oops. 1 and then press enter. And 0 and press enter. Close that down and we run, and it did not work. Not really sure why. Default gravity vector. That should have worked. Maybe it won't allow you to do gravity on the x-axis. Alright. Well, that makes for a particularly bad demonstration because I am not entirely certain why that happened. I should have applied. So anyways, I'll come back to that later. I'll probably put it as a comment exactly why that didn't work, because that is where you control your settings. Also, you saw that the gravity amount, that 98, the saying that it moves gravity, or gravity is applied at 98 pixels per second. Again, working in pixels makes things a lot simpler. So yeah, that's the basics of dealing with a kinematic object. Now let's look at a static in the same scene. Now let's go ahead and, so root selected, and let's just add a static body, like so, as something to collide with. Now I'll tell you right up front, this isn't going to work. So don't be really disappointed when I press play and it doesn't do what you want. But don't worry, I will show you exactly why at a later point. Let's load in our icon. All right, so once again, a static body is not going to move. So gravity is not going to be applied to it. It's just going to sit there. And this one is going to come and fall. And in an ideal world, hit it and respond. And in our world, not. It's going to pretty much just go right through it, to be honest. So let's check. So you can see our static body is not moving. That is the point of a static body. It is just a thing in the world that you can hit. Whereas our kinematic body is obviously moving. So now that that's done, let's now make it so that it collides. And in order to collide, we're going back to our collision things again. The exact same thing we did collisions earlier is what we need is a collision shape. We need to be able to tell the physics engine how this thing is shaped. So we go back to our rigid body here. Just go ahead and we apply either a collision shape 2D or polygon 2D. And we'll start with a shape because we start off, we're a pretty squarish looking thing. Like we've got slight corners here, but for the most part, we're a square. So we just added this collision shape onto our rigid body. Now we just need to come over here and define the shape. So let's go over to shape. Now for one, there's a bug here. Never pick line shape. For some reason, you pick line shape, Godot gets really angry, goes on strike for a little while, doesn't ever come back. So yeah, don't select that. It seems to be a bug. By the way, if you're the Godot developers listening to this, it appears to be a bug with line shape 2D. Don't pick it. So we're going to go back to our rectangle shape. And now all we do is define that shape. So it pretty much, oops, bugger. All right, undo that. Define that shape so it covers our object like so. Now we come down to our other guy over here and static, make sure it's a static body and not the sprite. With the static body selected, we just go ahead and do the exact same thing. And I'm not sure what I'm doing here. Let's go ahead and create our rectangle shape. And position it roughly. All right, like so. Now we go ahead and run this. Boom. And there you go. There's how collisions are now handled in Godot by the physics engine. It's really that simple. You just basically create either your rigid body, your static body, or your kinematic body. You give each one a collision shape, and that's it. Now, one thing you might notice here, though, is first off, my precision wasn't that great, and that's why they're not directly on top of each other here. So if you wanted that to work better, you would have to. Here, let's fix that a bit. Yeah, collision shape. Come on. And over here, that'd be a bit better. So now when they hit, they will actually hit. Now, a lot of times, though, you'll have shapes that aren't quite so, say, square. And then in that case, what you want to do often is actually use a convex polygon. So what I'm saying is more or less you want to define the outline shape of it using polygons. And thankfully, and this is something that's often quite difficult in other things because you got to come up with the damn polygons to figure this out in the first place. In Godot, it's really simple. Let's go ahead and we'll delete our collision shape right here. Go back to our static body, and we're going to instead make a polygon that goes around all the edges. And that is by creating collision polygon. All right. Now this guy works a little bit different. So now you'll see up here, you have this little pen now. Using the pen, you can define the boundaries of the collision. So let's do that. And now I just come down here, and I go click, 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 click. Guess I don't have to say click every time I click, do I? At this point, I kind of do. It's a compulsion. Click, 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 and click. There you go. So now we've created a bunch of polygons that are actually going to define the a more precise collision mesh than what we had with just a straight rectangle. So now we go ahead and run the simulation. It's going to behave a little bit different. See? Because the two surfaces are different. So more or less, it's exactly the same as you did with collision, but fortunately with Godot, there's a bunch of tools set here, like this this polygon definer here. There's got to be a better name than a polygon definer. But this collision mesh builder, that's what we'll call it, for creating your collision polygons. It's built in. It's a tool that's right there. So if you have complex sprites, that's all that it takes to handle them. And let's now go back. Let's zoom out a bit. Let me show you the effect of a couple of these properties. So go back to our rigid body up here, and let's change a couple things. Let's make it a lot heavier. All right, and let's make it a lot bigger. Actually, you know what? If you put really stupid values in, you're just going to make the world not happy. All right, let's go 300, and we'll keep 300. Why are you not editing? 300, enter. And we'll put our weight at 150, enter. Oh, so they're linked. Okay. Now we run it. Not really that exciting. Let's change our restitution or our bounce amount up. So now it's going to be bouncy. Ooh, and at a value of 1, more or less, you're going to go off with equal force that you came in at. This demonstration is not going to show you friction very well because of the fact that there's no surface to really slide on. Let's turn our bounce down to, say, 20%. And go ahead and run that. And now you'll see it bounces back up a little bit. And let's change this up to 0.5. And you'll see it bounces off a little bit more. There you go. And then each contact will be simulated. There you go. And at the same time now, I can also come back in here, grab this guy, and grab this guy and click sleep. Oops. Here. It's now asleep, and we run it, and nothing happens. This allows you to turn it off and on in code, so you can just as easily just grab a reference to the rigid body 2D and turn it to not sleeping. Anyway, so go ahead and do that. Is there a script attached to anything yet? No. So let's go ahead and go. I gotta start using better names. Let's say set process. Oops. It's true. Get rid of this guy. Oops. Get rid of all these things. And then we will go func process delta and if input dot is key pressed key underscore space self dot is sleeping set sleeping false. So now nothing. I hit the space bar and nothing. This is not turning into the greatest demonstration ever, is it? Hold on one second. All right, I'm back. I actually have no idea what actually this issue is. Um, my my script just wasn't being called for some reason. So when I deleted my object, created a new script, created the exact same code, it worked again. So I'm guessing it's some kind of a Godot bug that for some reason that script wasn't hooked up properly. But like I said, I just went ahead and recreated the same thing, exactly the same. And then I use this code here. So as you can see, you can turn set sleeping to false, and then it runs. So if you run into a similar problem, it might just be in your best interest to just recreate your code. I'm not sure exactly what just went wrong there, but as I said, the ready call was just not being called for that script attached to that node. So I don't know what happened there. I just deleted it and recreated it, and it works just fine. So I'll leave that one as a head scratcher. But anyways, back to the topic at hand. This sleeping then can turn on and off your physics entity. So rigid body right here by default is set to sleeping is on. We come back here, we see our game like so. Then I press the space bar and sleeping is off. Like so. So actually, I guess I should toggle this to that way. And go ahead and run that. And then now spacebar will turn it on and off. There you go. So sleeping is very handy if you need to have things that are being simulated, not simulated, simulated, not simulated. It allows you to toggle between them. Decreases the processing power extensively when you do so. Very handy functionality. The final thing we're going to show here is the kinematic sprite. And we'll use this exact same simulation. Let's throw one more guy in here, and we'll put him right around here. That will be a kinematic body. Like I said, kinematic body is often going to be used for your character. And let's go ahead and we will add a sprite as well. Guess which one? But you can't. Let's see. Load. On. Like so. Once again, we are going to need a collision shape or a collision polygon to do the detection. I'll just go ahead with shape because I feel lazy. I don't feel like saying click, click, click. Where did you go? The collision shape. And we're basically a rectangle. About there to about, say, there. All right, so now we have our new kinematic body. Go back into our world like so. You'll see, oh yeah, this guy. Here, I'll turn that sleeping off because I don't want it to be actually sleeping. So wake up, Susie, and go ahead and run that again. You'll see our physics goes on like normal. Our kinematic body is kind of behaving a bit like our static body, but it's not a static body. It's just waiting for input. So the physics system itself isn't going to affect it until we do something to it. So let's go ahead down to our oh, I wonder if I want the kinematic body paired the other way. I might have to change something in the future. I apologize if I have to. Just one sec. So let's attach a script to our kinematic body. And then we'll call it my character and create it. All right. Like so. Okay, sorry for a bit of a pause there. For some reason, it did it to me again. For each time I'm creating a new object, it's not actually calling the ready function. So I had to delete it and create it all over again. I think I have a bit of a bug going on with this project, so hopefully I'll just power on through. But a couple things to show you here. So we've created our kinematic body right here. And now I finally got the script working right for it. And go over here, here's the script, very simple. But we're just saying, yes, we want to handle processing. Then each time in processing, we're going to do a direct move call. This move function is part of our kinematic body 2D. So as you can see, there's right in here for moving and moving to, and also there's a check to see if it's colliding or something. So then you can, in your code, check for collisions and handle them accordingly. Obviously, you can also check and set a lot of the collision details as well, and then get the details so you can check if it is colliding, and if it is, you can figure out where it is colliding, etc. in your code. I'm not going to handle any of that right now. I don't particularly need to. There's another thing I'm going to show you here that I use all the time that I find really infuriating with the way Godot is set up. Is notice that we've got this compound object made up of uh, these three different things. And this hierarchy is very important. So you obviously want to move it together. And all of the transforms, as we've seen in the past, are relative to the parent. So you move the parent, and all the children follow. Now, what happens when you want to move the parent? So I click over here. So I've got the sprite and collision shape attached to this kinematic body. I want to go ahead and move this kinematic body. Yep. So I go over here, I grab it, and hey, you bastard, you selected the collision shape instead. And that gets really annoying really fast. There's two ways you can deal with this. You can first off set it to behind the parent. And behind the parent. So now when you come here and select kinematic body and you mouse, you get the wrong thing. All right, that's even more annoying. That's what you're supposed to do. So that's not normally the approach I take. That's for doing the Z ordering of how things are shown. But what I normally do is I pick the things that are getting in the way, such as my collision shape. Once it's defined, you don't really need to select it again. So just come on up here and hit a lock on it. Ditto for your sprite. Once it's defined, don't really need to change it, hit a lock. So now when you select, you will get the kinematic body because the other two are locked. And then if you need to unlock them, simply select them. Click the unlock. So handy little tip for selecting things as a group. Just lock the children, and then it will give you the thing you want. So anyways, back to our code at hand. So remember the simulation setup. So this guy will fall down and basically rest on top of this guy. Now we've added this this kinematic body here. And the idea again behind a kinematic body is that you can directly manipulate it. It's not part of the simulation, but it can participate in the simulation. You're about to see how that works. So our code then simply moves it by 0.1 pixel per update. Again, this is going to call it like 60 hertz, so that's 60 pixels per second at least. And let's go on back here and see what happens. Oops. All right, that's not a very good simulation. I'm going too fast. Let me just lower that down a little bit to maybe that much. And this will allow us to fall in time. Our object falls and rests, and our character comes in and hits it. Now you notice not much happened when we hit it. You would expect it to have gone flying or whatever. Well, that's part of when I was screwing around earlier. Let's go back to this guy. Remember let's see, rigid body. No, that should do it. Okay, that's not the one I screwed around with. Oh, all of my settings are gone. All right, so let's give a very small amount of bounce. And there. So now we're responding to it. Ditto, if I go down to our main guy, rigid body, and let's just decrease its mass. Somewhat substantially, and run this. You will now see, why are you not participating more? Okay. Well, anyways, first off, remember this oddity going on right now is because I haven't defined my collision boundaries very well, so they're overlapping and they're hitting even though the images themselves don't. I think it's boiling down to your kinematic body is not actually participating at all with the other things. So it's colliding. The kinematic body can collide with other objects in the scenes, but it's not actually affecting them, which is kind of irritating. And those are basically your three different sets. So once again, your rigid body, this is your fully simulated, has full calculations, physics entity. Your static body stays still, mostly just there to be hit or to interact with. And then your kinematic body, which is there for you as a programmer to move, and it can run around the physics world and collide with things, but that's about it. Now, let me actually just show you the scripts on that one. So we're moving now, and we'll just do if is colliding is true, and then we'll just simply go collide, like so. So programmatically, you're going to have a lot of times, like if it's colliding with another entity, and then another thing you can do, you can also get what it collided with. So this allows you to say, oh, did it collide with something? Oh, was it a bullet? And that could be somewhat important information for your character to collide with something. What was my error here? End of line. Oops. All right. So now we go ahead and watch down here, and when we hit collide, and we're still colliding, and we're still colliding and colliding, and so that's spamming over and over and over again. Eventually they should stop colliding. There we go. And its movement logic kicks back in. The physics object continues to fall. This actually isn't updating anymore. It just isn't clearing out. And that's it. That is the different interactions. Now, there's a bunch of things I haven't actually covered here, and we're already sitting at 50 minutes, so I'm not going to be covering them, at least at this point in time. There's a few more kinematic things to be aware of. Let me just see if they're all together. You can have areas or triggers, so you could have part of the map. So let's say end of level zone. It's not physically a thing there, but you want to trigger when something collides with it. There is the option of putting those things in. That's your area 2D. Let me just come and bring it up and show you. Area. So, as it says here, general purpose area detection influences for 2D physics, spelt wrong. And this is just the key things are you can set the signals or callbacks on a body enter and a body exit. So you can use an area to define, again, a trigger, a zone. So when something passes through it, you can have it call one of these three signals or emit one of these three signals. So you could know, you could have the character hits the end zone, the game over area, the pocket in a pool simulation, etc. Kind of handy there. Again, I'm not going to get into it in much detail. Then the other thing that we've got, I don't know where they are, is your joints. But joints actually appear to be all under spatial, so that's 3D only. Yeah, there we go. You've also got joints. Joints is a little bit more complex than we're going to get into here. But you have things like, well, a joint, like a pin joint. So you could do things like simulate a rope falling around a pivot. You've got a damped spring, which is for simulating a springing effect. Then you've also got the groove joint. This is useful for making a body slide through a segmented placed in another. I'm not entirely sure what you're going to use a groove joint for, but there are these other advanced physical options for doing slightly more advanced calculations. Things like, again, simulating a rope or a spring or etc. They are available there. The same basic logic applies though. You define it, you create the hierarchy accordingly, and then the simulation just takes care of it. So there's a lot covered there. There's a lot, unfortunately, we didn't cover there, but as I said, we're getting up there in time. I hope that was useful to you. So quick recap of what we covered here. First off, we did collision detection. Collision detection doesn't need the physics engine at all. Essentially what you do is you create a shape 2D derived object. We use the rectangle shape 2D, but there's also, again, circle and capsule and then polygon ones. And you use it for just calculating collisions between two objects. You use the isCollide, and you just test the two shapes and the positions of their parent containers if there's a collision occurs or not. Now, if you need a more advanced situation, then you get into the physics engine, which we saw here. The physics engine has the three basic types. The static body, which you can think of as a full physics object. Sorry, the kinematic, the rigid body, which you can think of as a full featured physical object. The static body, which is an unmoving entity in the world, but it can be collided with and interacted with by a rigid body and a kinematic body. And then finally, a kinematic body, which isn't really simulated physically, but can interact in the world, which means it can be moved around by you, and it can collide with physical objects in the world. Ultimately, this, again, is normally like your player's ship. That kind of stuff is controlled by a kinematic body, where you are controlling the motion yourself, not letting the physics engines take it for you. But you're still going to want to obviously collide with things that have physical properties. You want to be able to not run into obstacles, be hit by bullets, etc. And those are all controlled by the kinematic body. So the kinematic body does it. The physics engine handles all the other stuff, and that's about the extent of it. You define these things by making the top level physics entity and then attaching all the stuff to it. So if you want to have collisions, you need to make sure you add some kind of a collision shape, which either is a collision polygon, which allows you to precisely define the outlines, or it's a collision shape like we used earlier with the collision detection. If you use a collision polygon, there's a tool built in there that you can define them easily yourself. And then otherwise you just set up your physical entity, in this case the sprite, that is going to be controlled by the physics body, and as the physics body moves, it will then move the position of the corresponding sprite. Remember that the controls are in pixel units, so by default gravity is 98 pixels per second along the gravity vector. For some reason, changing the gravity vector did not work. We'll call that one a bug. But it might just be an error I'm making. I'm not entirely certain there. But that's the crux of it. That is Physics 101 in Godot engine, in the Godot engine. I hope you found that interesting. Stay tuned for more. Thank you very much. Goodbye.